Okay, so for family of functions and transformations, the study of calculus is heavily dependent upon understanding the behavior of functions. Therefore, it is imperative that we know how families of functions behave. So starting out with the first one, we have the absolute value of x. So you have to think about every input value that we put in, the output, we take the absolute value of. And that's why we end up with this V shape, because anytime we take the absolute value of 0 or any positive number, it's itself. But every time we take the absolute value of a negative number, it turns positive. So for all these negative input values, we have positive input values. And we know that whenever we graph an absolute value function, it is V-shaped. The next one is one we don't see as much. This is called the greatest integer function, or the step function. The domain for this is all real numbers. But the idea is for every number that you substitute in for the input, the range or the output is an integer. So it's the greatest integer, not greater than the input value. Pretty much what you do is for every value you substitute into it for the input, you round down to get the output. So the function looks like this. If we substitute 0, the greatest integer, not greater than 0, is 0. And then every value between 0 and 1, the greatest integer not greater than that value is still 0, like 0.5 or 0.6 or 0.999. But as soon as we get to 1, the greatest integer not greater than 1 is 1. So to show that they look like little steps, to show that it goes all the way up from 0 up to 1 has an output of 0, we put an open hole right here at 1. And then once you get the pattern going, you just follow it. For example, if I put in negative 0.5, the greatest integer, not greater than negative 0.5, is negative 1. So that's why we pretty much say it's kind of like what all you do is always round down. For every input value that you put in, you always round down to the nearest integer. And it looks like this. It can also be referred to as the floor function since we do round down. I'd like to show you that. So if you ever were to see this and instead of being the full set of brackets, it just has the bracket on the bottom part, it means the floor function, which means round down, which is still the same thing as the greatest integer function. But if you were ever to see the opposite, where the bracket is at the top, that is the ceiling function, which means that you would round up. And there's a lot of situations in the real world where we always have to round down to the nearest whole number or round up to the nearest whole number. The range for this is all integers. So since we can't write that as an interval, we use the symbol. And the symbol for all integers is Z, or you could write it in words, all integers, because the output is always an integer. That's why it's called the greatest integer function. And this is one that we don't see as much. All right, the next set, we're starting to get into our power functions. So y equals x squared, y equals x cubed, y equals x to the fourth, and so on and so on. So you may want to, make a little note in here. This is where the power functions start. This one is very basic. It is just your parent graph of a line, even though you've never thought about a parent graph of a line or a linear function. It goes through the origin. It's like saying y equals x plus 0, and it has a slope of 1 over 1. Then as we change that y-intercept, that's what moves it up and down. And then as we change the slope, that's what would reflect it or shrink or stretch it. The domain is all real numbers, and the range is also all real numbers. Where our next one, which is our parent quadratic function, graphs our basic parabola. And we know the input is, we can input any value. Our domain, again, is all real numbers, but the output is always the squared value of the input. And that is why our range is only 0 and positive numbers, because anytime we square a negative number, it becomes positive. As we go out 1 in each direction from the vertex, we go up 1. Out 2 in each direction, we go up 4. Out 3 in each direction, we go up 9. Because our range is those list of perfect squares, that 0, 4, 9, 16, 20, 25, and so on. All right, the next one is our parent cubic function, our basic cubic function. So it's also a power function, a power of 3. So now you have to start thinking about in terms of perfect cubes. Again, our domain is all real numbers. We can substitute any number we want in for x. There's no restrictions on what we can substitute in, but our range is going to be that value cubed. So 0 cubed is 0. 1 cubed is 1. 2 cubed, however, is 8. And I can't fit that on my graph paper, but I want to make sure when I draw this that it goes towards that 0.28. Don't draw this like this. Don't have it swing way out because that doesn't make any sense. And negative 1 cubed is negative 1, and negative 2 cubed is negative 8, which is way down here. So again, make sure it's going in that direction. The range for this function is also all real numbers. Then we go over to y equals x to the 4th. So again, no restriction on what we can substitute in for x. Our domain is all real numbers. And as we substitute values in, we are going to raise them to the 4th power to get our output value. So 0 to the 4th power is just 0. 1 to the 4th power is 1. But 2 to the 4th power would be at 16. And if we go on the other side, negative 1 to the 4th power is also positive 1. Negative 2 to the 4th power is also 16. So this is going to look like a parabola, and it has that parabolic shape. But what happens is it actually, once you get outside of that 1 or that negative 1, it grows much steeper than the one above. And the range would be from 0 to infinity. Now we could keep doing this all day long, but I just want to look at the pattern real quick of these 4 power functions. Notice that the ones that are raised to an odd power, the arms go in opposite direction. And that is because these are like your parent polynomial functions. Where the ones raised to an even power, the arms go in the same direction. And that is going to continue. If I said graph y equals x to the 21st power, it's going to look similar to y equals x cubed. It's just going to be it's going to grow a lot faster than it, but it's still going to have that similar shape. Where if I have asked you to graph y equals x to the 10th, it would be similar to that parabolic shape. It would just, once you get outside that 1 or that negative 1, it's going to grow much faster. So that happens with all power functions. All right, so now we're going to get into our root function. So here's where we start having to restrict our domain on this back side of this paper. All the functions on the front side, there was no restriction on the domain. But when we get to the square root of x, think about numbers in the real number system that we can't take the square root of. For example, negative numbers. That's where imaginary numbers came from. And imaginary numbers are not real numbers, guys. They're imaginary. We made them up. So the first x value that we are allowed to substitute into this function is 0. We can only substitute 0 and positive numbers into this function. So when we do that, if we substitute 0, the square root of 0 is 0. If we substitute 1, the square root of 1 is 1. Now if we substitute 2, the square root of 2 is the square root of 2. And I know about where that is, but I would probably rather get some nice points on here. So I'm going to think invertly for a second. It's kind of, this is the inverse of our quadratic function. So the next number I'd want to substitute in would be 4. And we know that square root of 4 is 2. Or then I would want to go to 9, and the square root of 9 is 3. And what we see is this is a sideways parabola, but it's only half of it, because we don't have that plus or minus in there. If we drew the whole parabola, it wouldn't be a function. And this is what our square root function looks like. The domain is the domain is from 0 to infinity, and the range is also 0 to infinity. However, for a cube root, we can substitute negative numbers. We can take the cube root of negative numbers. We just can't take even roots of negative numbers. So the domain for our cube root is from negative infinity to infinity. But we need to start thinking invertly from y equals x cubed. So if I substitute 0, the cube root of 0 is 0. When we substitute 1, the cube root of 1 is 1. The next value what we would want to substitute in would be 8, not 4. I don't know what the cube root of 4 is. I mean, I know about where it is, but I don't know what it is. You have to think of your list of perfect cubes, not your list of perfect squares. So we would have the 0.82, which would be down here. So this is going to look like this, where the cube root of negative 1 is negative 1, and the cube root of negative 8, I would want to go to the next perfect cube, is negative 2, which would be down this way, so it would look like this. And that is what the cube root of x is like. I know it's growing much faster horizontally than it is vertically. It still continues to grow vertically forever and ever, so the range is also all real numbers. All right, so then we get into our exponential and logarithmic basic functions, y equals e to the x and y equals natural log of x. So guys, remember, e is approximately 2.7. So if I need to come up with some points for this one, think about it. I'm just going to write over here real quick, x, y. When we substitute 0, any number other than 0 to the 0 power is 1. E to the first power, e to the 0 power, think about it right here, would be 1. When we substitute 1, we're just going to get e, so that's about 2.7. When we substitute negative 1, we're going to get e to the negative 1, which is really 1 over e. So think about that being approximately 1 over 2.7. Like we said earlier, if you can graph y equals 2 to the x and you can graph y equals 3 to the x, then we can graph y equals e to the x. 0, 1, and then it's going to go through the point 1, about 2.7. That's that 1e. And then at negative 1, it's like 1 out of 2.7. So that's right in between 1/2 and 1/3 there. And that is enough to get this graph going. We don't need 50,000 points on there. We know it's an exponential function. That horizontal asymptote is going to be at y equals 0. So the domain for this one is also all real numbers, like all exponential functions, but the range is from 0 to infinity, not including 0. All right, so for our next one, f of x equals the natural log of x, we know that that is the inverse of the e to the x function. That's how they relate to each other. They are inverses of each other. So if we understand the points on our y equals e to the x, all we have to do is switch them to graph the points on y equals the natural log of x. So instead of having the point 0, 1, we're going to have the point 1, 0. Instead of having 1e, we're going to have e1. So again, e is about 2.7. So we go over about 2.7 up to 1. Instead of having negative 1, 1 over e, we're going to have 1 over e, negative 1. We know that exponential functions have that horizontal asymptote at y equals 0. Therefore, the logarithmic function has that vertical asymptote at x equals 0. And so it's just going to look like this. Remember, an exponential function, any function in its inverse always reflect over the line y equals x. So if you were to draw these on the same graph, they would reflect over that line. The domain in this case is restricted. Logarithms do not have a domain of all real numbers. They have a domain of 0 to infinity, not including 0. And it has a range of all real numbers. Again, it's the whole idea of an inverse. What was the domain becomes the range. What was the range becomes the domain. All right, and then we have our rational parent functions that we learned back in section 2.4. So we have our 1 over x, and we recall the most important points on the reciprocal function is 1, 1, and negative 1, negative 1, and then we graph that basic function. And the same thing over here. The domain for this is all real numbers except for 0. So from negative infinity, 0, in union with 0 to infinity. Range is also the same because it's all real numbers except for 0. So negative infinity to 0 in union with 0 to infinity. And guys, at this point, let's talk about this. These graphs we need to know. We should not have to sit here and substitute in x values to figure out y values. You must learn these graphs, know the points, and be able to graph them quickly. All right, the last one we also learned back in 2.4, instead of it being the reciprocal function, it's the reciprocal of the square. So all your input values you're squaring and doing the reciprocal of. So it also has the point 1, 1. However, when we substitute in negative 1, we get positive 1 because the negative 1 squared is 1, and then the reciprocal of 1 is still 1. Now, what makes this one a little different is when we substitute in 2, instead of getting a half, we get a fourth. If we substitute in 3, we would get a ninth, because it's not just the reciprocal of, it's the square of the reciprocal. And this is a mirror image across from the x-axis. If we substitute in 1/2, we would get 1/4, negative 1/2, and positive 1/2. So this one looks like this. So some students think it's the same as the 1 over x in the first quadrant, but it's really not, because it's the output values are squared, not just the reciprocal of. And so our domain is all real numbers except for 0, and our range is only positive real numbers. Again, please make sure you study these, practice these. You will be quizzed and tested on them, and it will be within a specific time. You do not have time to sit there and substitute x values in to figure out what y is. You've got to learn these graphs. These are the very basics of what we're learning. All right, so then on the next page, transformations of functions. So I've already filled this in for you, but we're going to talk through it. Anything that we do outside a function affects it vertically. And we've already been talking about this quite a bit. We add, subtract, multiply, divide, put a negative outside that function. It is a vertical transformation, where anything we do inside a function is a horizontal transformation. And when we do stuff outside the function, I say it transforms logically. It does what you think it would. We add outside, it moves up. We subtract, it moves down. We multiply by 2, it stretches vertically by a factor of 2. We multiply by half, it shrinks vertically by a factor of half. Where the horizontal transformations do the opposite of logical reasoning. We add inside, it moves left. We subtract, it moves right. We multiply inside the function by 2, it shrinks it horizontally by a half. Not by 2, by a half. If we multiply inside the function by a half, it stretches horizontally by a factor of 2. So most of you are pretty good with these transformations. The one that I think is the most confusing is when we multiply inside the function. That horizontal shrink or compression or the horizontal stretch. And notice how it says by a factor of 1 over c. So it's always the reciprocal of the number that we're substituting in. So to help you understand that, we're going to look at a couple of graphs. Okay, so I'm going to start out with an absolute value function. And here's our basic parent absolute value function, y equals the absolute value of x. Watch what happens when I do y equals the absolute value of 3x. I'm going to turn this on real quick so you can see it. So even though you may look at it and you may say, oh, well, it's narrower, it's stretching vertically. It's actually not. It is shrinking horizontally by a factor of 1/3. So by looking at this table of values, I think you can see it. Instead of it affecting the range values, it's affecting the domain values. That's why we say it shrinks by a factor of 1/3, the reciprocal of 3. Look at these tables I've created for you. Notice that the y values have not changed. They have the exact same heights, in other words. But the x values from our parent function to our y equals the absolute value of 3x are all 1/3 of what they were. Also, look at it on the actual graph. Look at how you had the point -2, 2. And now you have the point -2/3, 2. Same height, didn't affect the y value. It's like it took that graph, that red graph, and it pushed it in, it compressed it to 1/3 of what it was. Same thing right here. Look at that 1. And you know what? I should put 3 on here because that would probably be an easier one to see. Look at 3, 3. And then look how on here you have 1, 3. I'll just change that to 1 real quick. So you can see how the x value is 1/3 of what it originally was. Did not affect that y value. Let's look at a different one. So for example, let's look at a square root function. So the red graph is the parent graph. And in the second one, we've multiplied inside the function by 2. So a good way to think about this is this graph, because we're multiplying inside the function by 2, it's now going to move twice as fast as it did. Think about like the x-axis representing time. So if it's moving twice as fast as it did before, it's going to take half the time to get there. It's moving twice as fast, it takes half the time. And look, you can see it on here. Normally we have the point 1, 1. Now we have the point 1/2, 1. Again, the range values were not affected. The domain values were. We're halving all those domain values. Normally we're at 4, 2. Now it's 2, 2. So the heights, and that's why I purposely picked out these points on here for you. The y values are the same. It's the x values that are halving. we didn't double the x values. We didn't stretch it vertically by a factor of 2. We actually shrank it. Sorry, excuse me. We didn't stretch it horizontally by a factor of 2. We actually shrank it horizontally by a factor of a half. Okay, so in this example, instead of using square root or absolute value, I'm using our basic parent quadratic function, which is our parabola. And you can see that right here in this red graph, y equals x squared. And there's our normal quadratic values. Hold on one second. Okay, there we go. So, you know, for all our inputs values, we square it to get our output values. So watch what happens to it when I multiply inside the function by a half. Remember, anything you do inside affects it horizontally. But instead of it compressing it horizontally by a half, it actually stretches it horizontally by a factor of 2. And again, this is kind of the way I think about it. If I multiply inside by a half, it moves half as fast as it did. So now it's going to take double the time to get there. So it stretches it horizontally by a factor of 2. And look, I purposely picked these values so you can see it. Notice how my y values are exactly the same on both tables. But my x values on the table, the second table where we have multiplied inside by a half, are double the x values here. And look at it graphically. We normally have 1, 1. We now have 2, 1. We normally have 2, 4. We now have 4, 4. Every x value you did have, you're doubling. The y values stay the same. And I feel like this is that part in this course where we finally start to grasp those horizontal dilations and how they affect the graph. Okay, so if you need to, go ahead and play with Desmos a little bit more. If you're having a hard time seeing it, you know, make up type in some parent functions and then perform some of these operations to them so that you can try to see how those transformations affect the graph. Look at not just it graphically, but look at the tables, look at it numerically, and see what's happening. And then when we meet back in class, we're going to do these examples together and perform these transformations together.